We'll now look at a new and unique type of compound called a coordination complex, formed with transition metals, but only formed in solution. To form this compound, one starts with a transition metal cation, in this case a silver +1, leading to a new definition of acids and bases. This silver plus ion is regarded as a Lewis acid. Because it has a positive charge, it can accept a pair of negatively charged electrons. Under this definition, any cation, either H plus or any positive metal, can act as a Lewis acid. In the solution, this Lewis acid is added to one or more species known as ligands. In this case, the silver ion is added to 2 ammonias. The ammonia, not surprisingly, is a base, and a new definition, it is a Lewis base, which is an electron paired donor. Anything with electrons can act as a Lewis base, so any anionic species, such as OH- is still a base. But additionally, any species with lone pairs of electrons, such as water or the ammonia shown here, can also act as an electron pair donor and a base, and be what is called a ligand. Once mixed, the Lewis acid and the Lewis base exist in equilibrium and form what is called a complex. In this case, the complex is shown as in square brackets Ag and H3 twice plus. In keeping with the main theme of General Chemistry 2, the first thing to note is that this is an equilibrium reaction. As an equilibrium reaction, it is defined by an equilibrium constant, where once again the subscript tells you what type of species you're looking at. In this case, the constant is Kf. It is called a formation constant to let you know that you're looking at a coordination complex. As always, this constant Kf, like every other equilibrium constant, is products over reactants as related by the balanced equation. So for this reaction, Kf would be equal to the concentration of my product, the complex AgNH3 twice plus, divided by my reactants, Ag plus and ammonia. And since I have 2 ammonias, the concentration of ammonia is squared. It is worth noting that since coordination complexes occur in solutions of the ligand, the formation constants are always very, very large and positive. These reactions essentially go to completion with the ligands just swapping out into the solution. What makes them special and different is the manner in which bonding occurs. If we draw out the Lewis structures, I start the same reaction with my 2 moles of ammonia, as shown here. You may note that each nitrogen in each ammonia has an unshared pair of electrons. To this, I add a metal cation, an ion with a positive charge. In this case, I add Ag+. I now have the unpaired electrons on the nitrogen attracted to the positive charge on the cation of the silver, and an equilibrium occurs with my product, as now shown. What makes this unique is that I have formed what is known as a coordinate covalent bond, a bond between each nitrogen and the central silver ion. This bond is covalent because, like every other covalent bond, I am sharing 2 electrons between the nitrogen and the silver. However, in a normal covalent bond, each species would donate 1 electron to share 2. In this case, as you can see, both electrons are being donated by the nitrogen by the ligand, and this is what makes it a coordinate covalent bond. Also of note is that the overall charge is maintained. I have 2 neutral ammonias and a silver plus, and the final complex has the +1 charge. There is no exchange of electrons. It's purely sharing. It is a covalent bond, except both electrons come from the same source. As we are talking about Lewis acids and bases, one may be reminded from General Chem 1 of Lewis structures in general in covalent bonding. Once again, in this case, knowing the bonding and knowing the structure gives information about the reactivity. In the case of coordination complexes, the structure is defined by something called the coordination number. This is the number of coordinate covalent bonds to the central cation. It is important to note that the majority of ligands only form 1 single bond. However, there are a certain few ligands that can form more than 1 bond. As a group, these are called chelating ligands, where the root chela is the Greek word for claw, because by forming more than 1 bond, these ligands can actually grasp and hold a metal cation. As usual, instead of remembering the majority of cases that form 1 bond, it's easier to recall the exceptions. The exceptions are 3 common chelating ligands. The first is the oxalate ion. As seen, 2 carbons, 4 oxygens, C2O4, 2-. As you can also see, the 2 single bonded oxygens each have a negative charge. Therefore, each one of those can form a bond, so the oxalate ion can form 2 bonds, 1 from each of the O-. And as there are 2 separate negatives, the overall charge on this ligand is -2. A second common chelating ligand to remember is called ethylene diamine. Again, the name and the structure are related. Ethylene. There's a C2H4 group in the middle, ethylene. Diamine, there are 2 nitrogens on the end, NH2. As each of those nitrogens has a lone pair of electrons, ethylene diamine is a dibasic ligand and can form 2 bonds. However, it is also a neutral ion with a charge of 0. The third common chelating ligand has a long name, but again is descriptive. Ethylene diamine tetraacetic acid, or EDTA for short. Related to the previous chelating ligand, you can see it's ethylene diamine with tetra 4 acetic acids. Each of the hydrogens on the ammonia is swapped with a C2H3CO2H group and acetic acid group. Since there are 4 acetic acids, it can form up to 4 bonds and is a very strong chelating ligand. As it is a weak acid in equilibrium with the conjugate weak bases, the actual charge is dependent upon pH and may be up to and including -4 if all of the acetic acids are ionized. Again, dealing with Lewis, the reason why it is important to know the coordination number is because if one knows the coordination number, one can determine the shape of the molecule. The coordination number directly tells you what shape the molecule, what geometry it will have, similar to what you've already learned about drawing Lewis structures in General Chem 1. If we look at the most common coordination numbers with the form or type of molecule they represent, the geometry becomes apparent. For a coordination number of 2, you would have a complex of the form AX2. The widest separation between the two ligands X gives you a linear molecule. Different from other Lewis structures, with a coordination number of 4, or a type of AX4, you have, usually, once again, a tetrahedral shape, as you saw in Lewis structures in General Chem 1. However, there are exceptions, and it is always easier to remember the exceptions than the rule. So once again, in this case, there are 4 exceptions. A coordination number of 4 with a central cation of either copper 2, nickel 2+, platinum 2+, or palladium 2+, will form what is called a square planar complex, which, as the name implies, everything is 90 degrees apart and planar, flat. Your third most common coordination number of 6, giving the type AX6, as with a Lewis structure, gives you an octahedral geometry. Also, like with any other compounds, naming of coordination complexes is important because, as always, the name of a chemical compound is unique and systematic. So if you know how to name one complex, you know how to name all of them. And if you have a name and you know the system, you can determine the formula. In the case of coordination complexes, as usual, it's first name, last name. One starts by naming the ligands first. If there is more than one type of ligand, they are named alphabetically by name. If there is more of one of the same type of ligand, the number of ligands of that type is denoted by a Greek prefix. For naming, as mentioned, ligands are Lewis bases, so they can either be neutral with unshared pairs of electrons, in which case the name is simply given. For common ligands, H2O is internationally known as aqua. Ammonia is commonly called amine. The other possibility for Lewis space could be an anion to donate an electron. Anionic ligands are named by using the root of the element plus the suffix O. For example, you know chlorine is group 7, so it always has a charge of -1. So a chlorine as a ligand becomes a chloro, a Cl-. After naming all the ligands, the metal cation is named last. In this case, you have ligands which can either be neutral or anionic, and a central metal which is always positive. So in adding up negatives, neutrals, and positives, your result for the complex can either be neutral, positive, or negative. If the complex is neutral or positive, one simply names the metal, followed by the charge or the oxidation number of that metal in brackets in Roman numerals. If the complex is negative, as a sum, one takes the root of the metal name and adds the suffix ate, A-T-E, where once again followed by the oxidation number in Roman numerals. So we look at some examples. You see a complex CO NH3 5 times Cl 2+. Your ligands are either NH3 amine or Cl chlorine. Alphabetically, A comes before C. And there are 5 NH3s, so this becomes a pentamine. As mentioned, since Cl is in group 7, it's a Cl-, so instead of chlorine, it is chloro. So you have a pentamine chloro. CO is cobalt. Adding up the charges. Ammonia has 0. Chlorine is -1. The entire complex adds up to +2. So cobalt -1 is +2. So the full name is pentamine chloro cobalt 3. To tie things together, there are 5 amines and 1 chloro, giving a coordination number of 6. This gives this complex a geometry of being octahedral. Moving on to the first complex we saw, AgNH3 twice plus. There are two NH3s, which makes it a diamine. Ag is silver. Ammonia has no charge. The complex is a +1, so the name is diamine silver 1. As there are 2 ammonias, and these are not exceptions, that gives you a coordination number of 2, which leads to a geometry to separate the ammonias that is linear. Third example, looking at all the possibilities. You see a complex Cr, H2O once, Cn, if you recall from General Chem 1, the cyanide ion 5 times with an overall charge of -2. Water is known as aqua. A comes before C. So this is an aqua. Cn- is a cyano, and there's 5 of them. So you have an aqua pentacyano. Chromium, Cr. But since the entire thing has a -2 charge, you have an aqua pentacyano chromate. Adding up everything on the inside, water is 0. 5 cyanides add up to -5. So chromium -5 gives you a -2. Therefore, for the charge and the full name, I have an aqua pentacyano-chromate 3. Five cyanides in a water adds up to a coordination number of 6, which gives me an octahedral geometry. A fourth example. ZnC2O4 H2O twice. From the previous examples, you saw C2O4 was an oxalate ion. This is significant. First of all, water being aqua comes before oxalate. There are two waters, so it is a diaqua. The oxalate ion, as you saw, has a charge of -2, so I have a diaqua oxalo. The entire complex is neutral, so Zn is just zinc. And again, since the oxalate ion is -2 and the charge is 0, I have a diaqua oxalo zinc 2. In this case, I have two waters, each one forming one bond. However, bear in mind, the oxalate ion was one of your exceptions, forming two bonds. So I have a total of 4 bonds, so my coordination number is 4. With a coordination number of 4, zinc is not one of my exceptions, so the geometry is tetrahedral. A final naming example. PT, NH3 twice, Cl twice. Once again, alphabetically, ammonia comes before chlorine, and chlorine has a negative charge. So I have a diamine, dichloro for the negative. PT is platinum. Ammonia adds up to 0. 2 chloride ions give you a -2. If the entire charge is 0, that means the platinum is +2 for a full name of diamine dichloro platinum 2. 2 ammonias and 2 chlorines add up to a coordination number of 4. And since platinum 2+ with a coordination number of 4 was one of your exceptions, this complex is square planar. This complex also bears further investigation due to what are called geometric isomers. I look at my PT NH3 Cl2 diamine dichloro platinum 2. Here you see a picture of that. Platinum 2+ in the middle, 2 ammonias on top, 2 chloride ions on the bottom. Square planar, meaning there's a 90-degree separation between each ammonia and each chlorine. But then if you look at this closely, you realize this is not the only way this complex could be drawn. Instead of ammonia, chloride, chloride, AA, BB, I could also draw alternating ammonia, chloride, AB, AB. These two molecules are examples of what are known as geometric isomers. As you can see, they are, first of all, molecules with the same formula, PTNH3 twice, Cl2 twice, and the same square planar structure. But they differ in the arrangement of the ligands. As mentioned, first case is AABB versus alternating ABAB. I have two compounds that look different. Therefore, they cannot be the same compound, and they cannot have the same name. In the case of geometric isomers, these are differentiated by a prefix. The first isomer is called the cis, CIS isomer. So it would be cis diamine dichloroplatinum 2, where cis is literally the Latin word for same side, as the ammonias are on the same side as each other and the chlorines are on the same side. The second isomer is called the trans isomer. So that would be trans diamine dichloropplatinum 2, where trans is Latin for across. To get from one ammonia to the other one, you have to go across the platinum. To get from one chloride ion to the other, you have to go across the platinum ion. Other geometric isomers are also possible. Take, for example, the complex FeH2O3Cl3. 3 waters before chlorine alphabetically, triaqua, trichloro, the entire charge is 0, ion 3. Shown is one way to draw this complex. If you look carefully in this drawing, you will see the 3 chloride ions form a triangle, and on the opposite side of the molecule, the 3 water molecules form a triangle. Those triangles are faces of the octahedron, since coordination number is 6. This is what's called an FAC isomer, or a facial isomer. So this would be FAC, triaqua, trichloro, ion 3. More subtle, but in the next picture you can see another way of drawing this molecule, where I've run chlorine on top, 1 on the bottom, 180 degree separation. In this case, the chlorines go the chloride ions go 1, 2, 3, top to bottom. The waters go 1, 2, 3, right to left. If this was a globe, the waters would be defining the equator. The chlorines would be defining the lines of longitude, otherwise known as meridians. Therefore, this is a MER, M-E-R, or a meridial isomer, and would be MER triaqua trichloro ion 3. In closing, for geometric isomers, you have 2 possibilities. The first possibility, you can form cis-trans isomers. These require exactly 2 identical ligands. The magic number you're looking for in the formula is 2. Because if you look back, cis next to each other was a 90 degrees separation, and trans across is 180 degrees separation between identical ligands. Cis-trans isomers are possible in square planar and octahedral complexes as long as you see the number 2 next to one ligand. They are not possible in tetrahedral complexes for simple reasons of geometry being geometric isomers. A tetrahedron has a 109.5 degree separation all the way around. Therefore, there are no 90 or 180 degree angles possible. The second type of isomer, the facial meridial isomer, is more specialized. It requires 3 identical ligands to change the geometry. Therefore, it is only possible in octahedral complexes. So if you see an octahedral complex with the number 3, it can form facial or meridial isomers. Moving on to how structure informs behavior. We are specifically looking at transition metal coordination complexes, where transition metals fill the d orbitals. In General Chem 1, you had seen the shapes of orbitals, where an s orbital was round, p orbital was a figure 8, either facing on the x, y, or z axis. To fully understand how transition metal complexes work, one must first look at the d orbitals. So we start by looking at there's 10 electrons, therefore 5 orbitals. So we set up 5 sets of x, y, z axes. The orbitals are named as follows. They look like 4-leaf clovers, and the first one is dxy, where you have a clover sitting on the xy plane bisecting the axes, 45 degrees in between x and y all the way around. Basically, an X laying flat. DYZ, again, 4 lobes of the clover, bisecting the YZ plane. An X standing up, going front to back. DXZ, switching the X, your 4-leaf clover now sits on the XZ plane, essentially an X standing up left to right, again 45 degrees between all the axes. Your 4th d orbital is called dx squared minus y squared, where you once again have a 4-leaf clover, except this time the leaves are sitting directly on top of the x and the y axes. The final orbital looks different and looks odd. It's the dz squared, where you have a figure 8 on the z-axis with a little donut around it. This is what the orbitals look like. What they managed to do geometrically is form 2 sets. You may notice a relationship between dxy, dyz, and dxz. In all 3 cases, the 4-leaf clover bisects an axis. It sits 45 degrees off normal on the xy plane, the yz plane, or the xz plane. The last 2 orbitals, dx squared and dy minus y squared and dz squared, sit directly on top of the axes. These geometric considerations actually have a very large impact upon how complexes behave and why they're interesting. This comes down to something that is called ligand field splitting. I start with some complex, Ml6 plus, with a coordination number of 6. This is octahedral. So once again, three-dimensional space, I draw my axes. To make this complex, the metal cation sits at the center, and to get 6 ligands, you wind up with a ligand on the end of each axis. 3 ligands, top, bottom, left, right, front, back, gives you 6 positions. Now this is where everything comes together. You remember, by being a Lewis base, a ligand, each ligand is donating a pair of electrons. And previously, you saw that the metal D axes are grouped, where some orbitals rather, lie directly on the axes. Specifically, the dx squared minus y squared and the dz squared. Also remember where the orbitals come from. All orbitals, including the d orbitals on the metals, hold electrons. So now you have electrons on the ligands and d orbital electrons on the metal. Electrons are negative. What are they going to do? The ligand electrons will repel the metal electrons. However, since there's no physical place for these electrons to go, the repulsion from what is called this ligand field winds up splitting the metal d orbitals into 2 levels. So consider an octahedral complex. One starts with one's 5d orbitals, xy, yz, xz, x squared minus y squared, and z squared. Two of these, this will now become split by the octahedral field, as you previously saw. Also, as you previously saw, 2 of these orbitals, x squared minus y squared and z squared, are directly in contact with the ligand. So they will be repelled and pushed to a higher energy. Since energy must be conserved, the 3 remaining orbitals, xy, yz, and xz, will be pushed to a lower energy. Similarly, if one takes a tetrahedral complex, for similar reasons, you start with your 5 orbitals, xy, yz, xz, x squared minus y squared, z squared. They will also split. However, the geometry in this place, or in this situation, winds up being reversed. In this case, xy, yz, and xz are directly exposed to the ligand electrons and get pushed to a higher energy, and x squared minus y squared and z squared get dropped to a lower energy so that the total net change is 0. This splitting is essential to the behavior of complexes. The size of this energy gap is named delta 0. More important than the name, the size of the gap is actually determined by the ligand. So here we look at some common ligands. We start with what are called strong field ligands, meaning ligands that lead to a large delta zero. On your common ligands, the strongest is the cyanide ion, followed by the nitrate, ammonia, the thiocyanate, water, fluoride, chloride, hydroxide at the end, which is now a weak field ligand leading to a small gap or a small delta zero. This gap gives rise to all of the physical properties of complexes, which are varied and interesting. For one thing, transition metal complexes generally have color. How this occurs? Taking a look at a simple complex, TiH2O6 3+, with a coordination number of 6. This is an octahedral complex. And titanium 3+ means it has an electron configuration of argon 3d1. So I start off with my 5d orbitals with 1 electron. Since it is an octahedral complex, this will be split 3 orbitals down, 2 up. And by the Aufbau principle, my lonely electron will sit on the bottom. However, if I shine a light into this solution, one remembers from General Chem 1 that light has energy. E is equal to Planck's constant times the frequency. Energy can be transferred, energy can be absorbed. If the light has the correct frequency, the electron can absorb that energy and move to the next energy level. It can go from the bottom up to the top. What is essential in this case is that the energy of the light, h times the frequency, must be equal to the crystal field splitting energy of delta zero. One can look at this, first of all, qualitatively. If one has a strong field complex, a complex made with a strong field ligand, that is a large delta zero which will absorb a high energy photon. From light, Roy G. Biv, violet is the highest energy photon. And since colors are complementary, if I am absorbing the violet photon, what is left over, the solution will appear to me to be red. At the other extreme, if I have a weak field complex, a complex made with a weak field ligand, that will absorb a low energy photon. Red is the lowest energy, so conversely, if I remove red from the spectrum, the solution made by a weak field complex appears blue or violet. I can go further. Quantitatively, I can measure that this complex, hexaaqua titanium 3, absorbs light at 510 nanometers. Knowing that information, I can determine what is the value of the crystal field splitting energy, that distance, that gap. By remembering that if light gets absorbed, the energy of light, h nu, has to be equal to the crystal field gap, delta zero. In this case, the energy of light, h nu, is h, Planck's constant, 6.626 times 10 to the minus 34th joule seconds. I was given a wavelength, so h nu is equal to hc over lambda, c, 2.998 times 10 to the 8th meters per second. 510 nanometers, meters on top, match meters on the bottom. 510 times 10 to the minus 9th meters gives me an energy of light of 3.895 times 10 to the minus 19 joules. One must remember this is the energy of one photon of light to move one electron. So the actual crystal field splitting energy, delta zero, is going to be that energy for one photon, 3.895 times 10 to the minus 19 joules, times how many electrons equal a mole, 6.022 times 10 to the 23rd. So for the complex hexa-aqua titanium 3, delta zero by the spectrum is found to be 234,560 joules per mole. An additional and final interesting property of coordination complexes are their magnetic properties. This arises from basic physics. First of all, one should recall that electrons are circulating spinning charges. By general physics, that means each electron is an individual tiny little magnet. As magnetism is polar, north-south, south-north, paired electrons will cancel. However, unpaired electrons contribute to the net magnetic susceptibility of a material or its ability to be attracted to a magnetic field. Which leads to the following definitions. Paramagnetic, the thing that one thinks of as sticking to other things, is something that is attracted to a magnetic field, in other words, that has unpaired electrons. At the opposite end, diamagnetic, something that is repelled by a magnetic field, has no unpaired electrons. As unpaired electrons contribute to magnetism, the magnetic susceptibility is determined by the total number of unpaired electrons you have, which is called S, the total spin. Remembering, for quantum numbers, electrons have a spin value, m subscript s plus a half or minus a half. Therefore, for any system, the total spin is going to be the sum of all the m sub s's, the sum of all of those plus a halves or minus a halves. So using this, how is magnetism determined? Two complexes. A question. Which of the following is more paramagnetic? FeCN6 3 minus, or FeOH6 3 minus. This is also an example of why naming is important. If I name these complexes, it makes things easier. FeCN6, 6 cyanides, cyanide having a negative charge. Hexacyano, the entire complex has a negative charge, so instead of iron, it gets the suffix ate. So it is a hexacyanoferrate 3. The other complex, OH minuses, are also negative and are hydroxides. And as there are 6 of them, I have a hexahydroxoferrate 3. So, I look at the names. What do they have in common? First of all, at the end, they are all 3. Iron plus 3 has a charge of argon, has a electron configuration rather of argon 3d5, which means with my 5d electrons, 5d orbitals, I have 1 electron in each orbital. Secondly, at the beginning, you notice hexa. Hexa, coordination number of 6, means they are all octahedral, which means they will all split 2 up, 3 down. I look further. Now for the differences. In the first case, Cn minus cyanide is a strong field ligand, meaning I have a large crystal field splitting energy, meaning by the Aufbau principle, I got 3 electrons are going to go on the bottom. On the other hand, OH minus is a weak field ligand, which gives me a small delta zero. With 3 electrons again go on the bottom. So the question, where do the next 2 electrons go? In the cyanide complex, I have a very large crystal field splitting energy. It is difficult for the electrons to reach the top level. Therefore, I will wind up with the maximum amount of pairing and what is known as a low spin complex. In the second case, since the gap is small and electrons generally do not like to be paired unless they have to, the remaining 2 electrons can go on top. I wind up with a minimum electron pairing and what is known as a high spin complex. So if I add up the spins for the cyanide complex, I have plus a half, minus a half, up, down, plus a half, minus a half, up, down, and up. That gives me a spin of 1/2. However, for the hydroxide complex, 5 electrons, plus a half, plus a half, plus a half, plus a half, and a half, gives me a spin of 5/2. Therefore, definitively, the more paramagnetic, although both of them have unpaired electrons and are both paramagnetic, the hexahydroferrate 3 is more paramagnetic by a factor of 5. And this concludes the introduction to transition metal complexes.